But I think that's working. Okay, let's get started. Welcome back after the summer break. It's good to see everybody. So our first talk after the summer is going to be led by Peter Dueben and Matthew Chantry, who are joining us from the European Centre for Medium Range Weather Forecasting. And they're going to talk to us about deep learning and how it's being used to improve weather forecasts. So I'll hand over to you, Peter.
Okay, thanks a lot. Thanks for the invitation as well. So I'm going to kick off, and then Matt is going to take over, and then I'm going to kind of close again. So you will see both of us in the next 45 minutes. Um, Machine learning for weather and climate. I wasn't kind of quite sure where everyone from you was coming from. So I assumed that not everyone would know the ECMWF or the European Weather Center. And I have one slide, but we'll keep it very quickly, very brief here. So basically, the European Weather Center is an institution, an intergovernmental organization, and we have the aim to kind of really provide a medium-range weather prediction, which means a couple of days into the future, and we're focusing on global predictions. And we're doing this with our member states, and you see a map of the member states on the right. We're now having three sites. One of them is in Reading, the headquarters, and one of them is in Bonn, and the other one is in Bologna, where our supercomputer is stationed. So as we do operational weather predictions, we need a supercomputer and we also need a forecast system. So everyone who's kind of maybe heard about the IFS, the integrated forecast system, that is kind of our leading model that we're developing. And we now also made the switch into the AIFS, the artificial intelligence forecast system that Matt is going to talk about. And for those of you who do machine learning, you probably also will have heard about the ERA5 reanalysis dataset that is also developed in our kind of institution. So we kind of do all these kind of things, and we have really the focus on this kind of global modeling features and then global predictions. I'll give a very brief overview about the domain in principle before we dive into machine learning. So kind of big question, if you want to do kind of weather predictions, we need an Earth system model. And the question is like, why is Earth system modeling principle so difficult that you need a full institute to kind of do this? And the reason is basically because the Earth is first of all very large. So if you want to describe anything in there, you basically with a computer, you basically need a big supercomputer to have sufficient resolution. The Earth is also very complex in a sense that you have a lot of different components interacting with each other, and you also have a lot of processes that are kind of small scale. So normally clouds are smaller than 10 kilometers, but 10 kilometers is about the resolution that we use operationally, for example. So a lot of the processes that we need to resolve are kind of not um, it's not possible to resolve them explicitly. So we need to have so-called parameterization schemes that kind of try to mimic those small-scale features on the given grid that we have. On the other hand, we have a lot of observations and a lot of data about the Earth system. So we're getting something like 800 million observations into our institute every day, and we kind of use about 10% of them for operational predictions. Which means that we have a lot of information in principle about the Earth system, but this information also is very diverse. So you have kind of all sorts of sources. You have planes, ships, satellites, whatever. It's not that you have kind of the one data source, but really kind of a quite diverse zoo of information that's coming in. And for numerical weather predictions, we have kind of this workflow that we collect the observations in the first place. Then we do data assimilation where we kind of put the model and the observations together to generate initial conditions. And then we run the forecast model into the future. And then finally, we have post-processing and dissemination where basically the information is kind of still a bit enhanced before it goes out, and then it goes out to the user. And underlying the whole thing is really a high-performance computing application. So we have really supercomputers that we're running, and we're running among the fastest supercomputers in Europe and the world. Basically, we are also testing our models on those and run them there. So it's kind of quite a complex thing, a high-performance computing application in principle. And just to lay the scene of what was happening basically in the last couple of decades was that we had kind of a constant increase in quality of those models. So we basically, many of you will have seen this plot before. It basically shows how the forecast accuracy goes up for ECMWF forecasts over the time, and the x-axis is kind of years and decades. And you will see that all the lines are different color coded, are different forecast lead times, and all of them go up, which basically mean that we basically had like the forecast accuracy was increasing over time steadily during the last couple of decades. And that's often known as what we call the quiet revolution in numerical weather predictions. So we kind of knew that we basically, by constant investment into into numerical weather prediction in principle, also kind of increasing compute power and resolution, also by having more and better observations over the time, and also by using kind of better numerical methods in both the data simulation and the numerical weather forecast, we were able to kind of get better and better over time. However, we were kind of hitting a little bit of a roof in kind of a couple of years ago, where we basically said, okay, if we want to make the best out of our supercomputers, we kind of will be in trouble in a couple of years. And the reason is basically that the new supercomputers are kind of very much, well, back at the time we said that they are heterogeneous, but we really meant that they kind of have a CPU component or a GPU component, for example. So we have different hardware that we want to work with, and we also have basically the way how we could utilize this hardware really went down over time. So we started from something like running at at 50% of the possible highest performance we could get out of the hardware, and this reduced really to a couple of percentages in the 2020s. So it's kind of like really that we realized that we couldn't really make use of those big hardware systems anymore, and therefore we called for the so-called digital revolution. And the idea was here that we basically try to revise all of our models that we're doing in a way that we can really make most out of the high performance computing efficiency. So we would basically run the models, rewrite the models more or less from scratch in a way that we can really port them to different hardware, including GPUs. We would make them more efficient in terms of scalability and portability. And then we would also kind of include components such as machine learning, for example, into the mix. So that was 2015. And we knew that we would basically need a fairly big endeavor to kind of do something like this. And we've done this by having big programs in the European Union, for example, Destination Earth, where we really have like a lot of basically, we get a lot of funding to basically do this digital revolution and to run those models and redo those models. And then this should enable us to run the model at a resolution we call kilometer scale, which means that you go down from the 10 kilometers we have in operational systems today to something like 1 kilometer. And then you will be able to resolve a lot of the small scale features that are important, like, for example, deep convection in the tropics, and more the orography as well, that kind of the atmosphere sees when going over land, and all these kind of things that are kind of quite important and that we typically had to parameterize in the future, in the past. And it's now a stage that we reached basically where those kilometer scale simulations are reality, so we can run them on a daily basis, basically. We can also run them for long lead times, and they're kind of really clearly improving our forecast systems and kind of also like our forecast quality, if you want, of the small scales. So we talk about them as being so-called digital twins because they really kind of have a very kind of realistic representation of the Earth system in principle, and also domain scientists typically cannot really, well, put apart like data that comes from the model and data that comes from the observations in many cases. So that's kind of on the conventional side. And then there's machine learning, and I think Matt will take over now. Oh no, I'll continue to have a couple of more slides. Sorry. So machine learning came into the mix in something like 2018, and I bring the slide up again here. Because the slide kind of changes now. So with machine learning, what we basically have is a tool that can do a big mapping from inputs to outputs, and you can learn this mapping in very complex design. So you can literally have a mapping that has billions of degrees of freedoms if you want to, and you can learn this mapping from extremely big data sets. And that's kind of it. That's kind of what we do in machine learning, right? And in 2018, we kind of knew it was coming. We knew in other domains machine learning had a very big impact, but we were not quite sure how the impact would look like in our domain. So what we thought about was what could you use this kind of tool for in Earth system modeling? And if you kind of come back to the slide, you will see if you have a system that's very hard to describe in principle, in particular with analytical methods and also with high performance like with computing methods on a grid. And if you also have a lot of data available in various ways, and it kind of actually up to petabytes of data for modeling, then it's kind of quite clear that machine learning will have a bigger impact one way or the other. And this is a slide that I kind of produced back then, a couple of years ago, where I basically tried to kind of put all these kind of different application areas into the mix. And you will see that there are a lot of potential areas for machine learning in principle, and that they're also distributed over the whole workflow. So the color coding of the individual boxes kind of fits to the color coding in the workflow in principle. So that was a state of the art in something like 2020. And the domain scientists really thought about machine learning as kind of it should be used basically kind of to help the conventional modeling in one way or the other. But there's also another way, and now Matt is going to talk about the whole thing basically.
The other thing, thank you, Peter. We'll go on to the next slide and go through a bit of a timeline of sort of the last few years. Sort of 2018, as Peter already mentioned, sort of was where people were starting to explore machine learning for weather forecasting in all sorts of different ways, including trying to replace weather forecasting models. And Peter himself is partly to blame for this newfound system because as Era 5 was just coming out, so a brand new reanalysis data set, sort of quite considerably better than previous ones. He and Peter Bauer sort of explained one way it could be used in an interesting way to make weather forecasts. But they were a long way away from the IFS. They were a long way away from the skill of most sort of operational weather forecasting schemes. And so for a couple of years, it remained more of a toy or scientific exercise, sort of something where people are interested to see how they could push the boundary, but that was staying sort of quite considerably below the scale of the operational weather forecasting systems. And then in 2022, we had a very rapid development of those scores. So while there had been quite a considerable gap and one that didn't look to seem to be closing, we suddenly got a whole new loaded set of methods, some external actors who came to come and look at the problem, and the gap closed extremely quickly, with things first becoming competitive with GFS and then IFS, first in scores and then starting to be in derived products. And for a while, I tried to curate this slide, giving a timeline of the various developments as people moved onwards and onwards. And then I gave up because it just moves too quickly. Even though it's part of my job to stay on top of this, I'm aware of the papers, but curating this guideline is too much. But at ECMWF, we got to the point where we said, after doing quite a lot of internal analysis, this is the real deal. We think we are quite confident this is going to be part of how operational weather forecasting works in the future. We definitely don't know the balance of machine learning weather forecasts and physics-based weather forecasts, but we think it's important that we sort of enter this system, we start training our own models, and we start serving up data so that we and everyone else can understand really where the balance of this is going to settle. So next slide, please, Peter. So how does this work? How does training any of these models work? Again, sort of not sure exactly of the audience, so apologies if I'm speaking down to you here, but as Peter described, sort of machine learning, almost all of sort of machine learning, at least or a considerable part, is all about supervised learning. So you have an input, you have an output, they form an example. You ask your model to predict it, you score it on some metric, and then you do some back propagation to try and make it slightly better for that example. And the aim is over many examples going through them, you will get better and better on not just the examples you show it, but also the unseen examples. And training a weather forecasting model is no different in this scenario. You take two neighborhood time slices from Era 5. So you take a relatively complete set of the atmospheric state from Era 5, perhaps 13 pressure levels of, order 10 pressure levels of moisture, winds, geopotential height, temperature, and you ask the model to predict that same state 6, 12, 24 hours into the future. And then you go through the data set again and again and again. Typically, this takes sort of about 50 passes through the data set. This could be a couple of days or a couple of weeks to train, depending on exactly the model. But what people have found doing this is that this can get you to a very, very accurate model. So next slide, please, Peter. So I'm not going to spend too much time on the details of the AIFS, so the Artificial Intelligence Forecasting System, partly because that in itself could fill a talk and we wanted to make the scope a bit wider, but also because to some extent, right now, it doesn't appear to make the most difference exactly the architecture you use to build this. What seems to be important really is having a large enough neural network. So this is a neural network that has somewhere between sort of 10 million to somewhere sort of people are pushing this up to billions of parameters to fit. However, a key descriptor in lots of these is that there's a lot of sharing of the weights across space. So this is not about having a lot of learnable parameters individualistic for each grid point. It's about using a large number of parameters, but using those same parameters over the UK, over Australia, over the tropics, and asking the same model to learn how physical processes evolve across each of them. So the training scheme is, as I've described, there's a little bit more complexity to just picking two neighboring atmospheric states. Typically, what's happened is in these models is they're often trained to do a 6-hour step as their sort of first objective, and then you start to apply the model on top of itself. So ask to apply sort of f of x, and then minimize the errors over f of x, and then push that out a bit further, f cubed x, etc., and push that window so that you start to apply a model over a few days worth of an atmospheric state. And then perhaps some extra training on operational analysis because we have better atmospheric states now than ERA 5 due to it being a few years old. So next slide, please, Peter. So we're about to see that the scores are quite a bit better than the IFS, at least for some variables, and we'll talk about that in a bit more detail. But I'm going to get ahead of that and sort of ask the question, how is it possible, particularly given that ERA 5 is actually based on an IFS cycle that's a few years older than the modern IFS system, for training on ERA 5 to surpass the IFS? So next slide, please, Peter. So smoothing is one part of the answer. So by setting the problem up deterministically, which is how a lot of these models are trained at the moment. So that means trying to minimize a mean squared error over 6 hours, 12 hours, 3 days. You run into the fact that some of those scales are not predictable. And the models goes, well, I'm not going to try and predict extreme rainfall or extreme winds in those places. It'd be much better for me to smooth over that. I'm not going to get hit by the double penalty, and I'm going to therefore score better, get into a better object at minima. And you can see the output of this here. So we have two different time slices, but both are showing the same picture. So top row is at 6 hours, bottom row is 120 hours. On the left is the IFS, and on the right is the AIFS. And the broad thing to sort of see here is that there is a difference in terms of the representation of small scales, but otherwise the large scale features are broadly in very, very similar places between these models. So it's almost as if you've applied a smoothing filter, at least in this example, over the IFS to get to the AIFS. And this is one component of how you get to a lower score, but it is not all of it. So Peter, can you go to the next slide, please? So to go to another one, I wanted to look at an interesting test case where we had unseasonably warm weather over Europe, so particularly in Bonn, which I'm going to sort of discuss now. And this emerged from sort of the propagation of a Rossby wave train, so starting out over the Rockies. And this is an interesting example because sort of wave trains propagating over the Rockies are something that we know that the IFS is imperfect at. And so the IFS struggled a little bit in this test case of predicting that we would have this flow that we see down in the bottom, where you have the warm air being drawn up from near the Sahara, and therefore we have sort of quite unseasonably warm weather for particularly Bonn, where Peter is based. However, if we go to the next slide. Yeah, we'll see this in action, sorry. So this is showing forecast convergence. So this is forecast from increasingly back far away from a date, getting closer and closer and closer for a few different products. And you can see that the star in the top right is that we were hitting 24 degrees at the beginning of April. And there's lots going on in this plot. And I don't have time to go into all of it, but the key things I would point out here are the red dots are the IFS and the light blue dots are the AIFS. And the point is that sort of several weeks or a week and a half into this, the AIFS had this signal and maintained this signal that there was going to be very, very warm temperatures. So this is a demonstration of this fact that this wave train had been very well predicted and very consistently sort of predicted over the forecast horizon. So if we go to the next slide, I want to talk a bit about why that's the case. So ERA 5 is a set of 12-hour simulation windows. So what does this mean? We've done 4D VAR variational data assimilation to find the best trajectory, but it is a single trajectory that fits these observations. However, so this is a trajectory that the IFS can make. However, as I mentioned before with the AIFS, and in fact, this is sort of consistent across basically all of the large-scale machine learning models, they're actually asking to minimize errors over a longer forecast trajectory than just 12 hours. So they're minimizing over multiple data assimilation windows. And they're therefore trying to attain a trajectory that is well constrained by observations, but that we don't know an IFS trajectory that can get it. And this allows it to, for example, see how a wave train propagates over cycles when over DA cycles when when the IFS is unable to do it, or see how a tropical cyclone is affected by large-scale winds when again the IFS might struggle in inverted commas with notwithstanding all Peter's comments about how excellent weather forecasting systems are. So that's a far too short sort of quasi explanation of why we think these machine learning models are so good. So Peter, next slide, please. So how good is the AIFS? So this is a scorecard. So this is trying to be an aggregation over many, many variables of how the AIFS compares to the IFS. And broadly, what these are each sort of row, each column is a different variable, is a different region, and the blue is indicating that you have a improved score, and the red is indicating that you have a degraded score. But otherwise, most of you, perhaps all of you, have never seen the plot like this before. So we're going to the next slide and see a bit of context for what this actually means, what these colors really mean. So here is a scorecard from the last IFS cycle upgrade. So this is showing how good we were with a year's worth of many super scientists delivering that sort of increasing curve that Peter showed before. And the colors are the same here as they were before. And if we if I were to show you a web GUI of this, if we were to click one of these places, so for example, click on T850, in the bottom left is what you'd see. You'd see the anomaly correlation in the bottom left-hand corner of the screen showing an improvement. And above that, we would see the relative improvement is about 1.5 to 2%. So the tireless work of lots of scientists has very impressively delivered sort of 2, 3, 4, 5% improvements by perhaps improving resolution or improving representation of the physics, perhaps improving numerical schemes. But even in this scenario, a single cycle might not uniformly improve all the different variables all at once. So now with that, we'll go back to the context of, back to the AIFS and see exactly the same variable. I'm afraid the scorecards aren't exactly aligned because we made these with two slightly different versions. And I've zoomed in again on T850 for context. And you can see here, the bottom left, the control and the experiment, so this new cycle in the inverted commas with the AIFS, the lines are far clearer to be able to see the difference. And you have sort of a mixed signal where at 24 hours, there is quite strong degradation, which you can ask me in a question why that is. But after that, the signal is far bigger, sort of up to about 20–25% improvement in these scores. However, it's not all blue, right? So if Peter goes to the next slide, we'll see there's some clear, strong areas of red, some clear bands across this. So what is this? This is the top of the atmosphere. This is in the stratosphere, particularly at 50, 100 hectopascal, where these models are most of them are consistently worse than the IFS. This is one of the areas we're trying to understand how we can improve and why this is the case. So these systems are not ubiquitously better than the IFS. However, perhaps so far I've shown you 850, 150 hectopascal, and unless I'm not wrong, none of us live there. So we go to the next slide to actually see perhaps the variables that are of interest. So here is circled sort of 2-meter temperature, 10-meter winds, and total precipitation. And we can see that for the 2-meter temperature and 10-meter winds, the signal is quite clear. And this is against observation. So this is against an independent data set to both of these models. For total precipitation, it's a bit of a mixed bag. In the tropics, which is mostly blue, we see the AIFS is a bit better. In the sort of extratropics, either northern or southern hemisphere, the IFS is still quite a bit better in the first area in the first few days, and then the AIFS is a little better later. Although some of that certainly is corresponding to this smoothing. So next slide, please, Peter. However, scorecards are only really one facet of it. And I've already admitted that smoothing is part of this. And so one of the things that we've tried to do at ECMWF in building our own system is trying to get it out of the door as quickly as possible, because a weather forecasting model means very many different things to very many different people. And so you can now go to charts.ecmwf.int and look at a whole range of products and sort of see how weather forecasting phenomena is evolving. Or if we go to the next slide, you'll see that we have sort of open and live data, so coming out sort of 1 hour after people pay for it. So still very, very quick. And you can go and download the raw data for all the variables that are predicted and evaluate how these models are doing for the sort of test case of choice. Next slide, please, Peter. And I just want to, in this, sort of bring sort of focus to the fact that what we're doing is only sort of one element of this, and there's a whole rich tapestry of work going on at the moment. And one of the cool things I want to bring attention to is a collaboration we have with Met Norway, but now also expanding out with quite a lot of the national meteorological centers across Europe to see, well, how can this be done sort of in the most useful way for regional modeling? So this is describing a stretched grid configuration of the AIFS. So this utilizes the fact that the one thing I didn't tell you about the model is we use graph neural networks. So the cool thing about these is they learn to take data on a grid and map it into a different grid and do neural networks to map between those two. And so you can really play sort of fast and loose with mixing different data sets and getting it to learn how the correlations sort of work on two different grids. So we've created here a version that most of the place around the globe uses a global data set like ERA5 to train the model and then to initialize the model. And then over the region of interest, a region where we have high resolution data. So this is where for a few years, Met Norway have a couple of years of 2.5 kilometer data. We train on that to show the model sort of higher fidelity a solution, particularly when we're thinking about sort of winds or temperature profiles. And so here is it showing a little movie of sort of a weather forecast of this, where you can see this is actually an older version of the model, where it's actually 100-kilometer resolution, so really quite a coarse resolution outside of the area, and then sort of finessed up to 10-kilometer resolution over the Nordics. And you can see the advection of these fronts coming sort of from the Atlantic into the domain, and sort of by training the model end to end as a global model, one that has sort of resolution everywhere and just chooses to spend the computational resources over a region, you don't have to worry quite so much about boundary boxes or forcing, because the model is trained from an end-to-end perspective to do one specific objective. So next, sort of this is the sort of revolution that's in progress. Here's the sort of next one that we think is coming, and that is the question of can machine learning models do data assimilation or replace it? And you ask different people, you get quite strong arguments either way as to whether this will or won't succeed. So several of Peter and my colleagues are very convinced that this will not work. And the reason for this is that they say significant parts of the atmosphere are not directly observed. So training to go directly from observations to make a forecast will be a very, very hard task because we have gaps in observing network, particularly for sort of certain variables, certain heights of the atmosphere. Others are more optimistic. They argue, sort of, Peter mentioned earlier about how we're only using 10% of the data at the moment, that we have in our current data assimilation frameworks reasons to throw away significant data or make significant approximations in order to achieve a timely sort of a data assimilation product. And so I'm going to talk about sort of a couple of different approaches to how you can go about framing this data assimilation problem. The first is shown here in a bit of a diagrammatic sort of version. So the top is how data assimilation works from a conventional sort of equation system. So we would have sort of forward operators that help us move between observations and sort of the model states that then allow us to constrain the strait through a background that's evolved, and then through a data minimization process is sort of finessed into the best possible state of the atmosphere. That's then run through a forecasting model, which we've already seen. There are versions that can replace this element to then produce sort of future forecasting systems. And broadly, the machine learning approach would try and sort of slightly rejig this version so that it would say, actually, we can combine sort of forward operators and the state estimation into a one thing that then tries to estimate a sort of latent state of the atmosphere. This might not be a state that we can really probe directly ourselves, but we connect that to a neural network that then does the forecast and then allows us to read out this state. So this sort of means what you're doing is really training a system from end to end so that your initial conditions are observations and your truth at the end is observations, and you aim to minimize the errors from one to the other. And you could add era 5 into the mix as well as a halfway house to check that you've reached a good sort of state of the atmosphere. But you could choose to bypass this entirely and train a model that sort of seeks to sort of just use observations in training this. If you want to read more, particularly about this most extreme version, I recommend McNally et al., which is sort of more trying to set out a position of how you might go away framing the problem. So what's the state of the art for this at the moment? So I'm going to show you results of two variants of this. The one on the left is sort of mostly internal ECMWF effort. So what we have here are a few AIFS and IFS sort of 2 meter temperature scoring errors, which are the lines. And then the dots here are where we're at the moment with observation global forecasting. And you can see that we're in the right space, we're in the same neighborhood, but at the moment there's quite a considerable gap between the observation-based system and the physics-based system, or the sort of forecasting with machine learning, the AIFS-based system. So this would say we have not yet successfully replaced data assimilation with machine learning. On the right is work primarily coming out of the University of Cambridge, Vaughan et al. And they are doing something framed very, very similarly, but they use era 5 as an additional sort of handle or crutch on the data set. So if we were to, that's thinking of putting era 5 in as an intermediary state. So you break the model apart into a data assimilation module, a forecasting module, and then eventually you train all of those end to end. And here they compare to both sort of GFS and HRES. And the summary of where this is at the moment is it's competitive with the GFS across most of these variables, but lags behind at the moment the IFS. So to summarize, sort of like the scores are coming down. And if we went back to the timeline, if you're optimistic, you can say this is like the Ryan Keisler paper at the beginning of this sort of thing, because Ryan Keisler, who sort of kicked off the sort of last few years worth of activity, his headline of his paper was becoming competitive with GFS. Or you could still be quite skeptical and say sort of getting close is good, but actually it's going to be really hard to do those last efforts. So I don't think anyone's really being certain about where this is going to last. I'm an optimist. I am in every part of my life. And I think I see that the additional data that we can still add into this, the additional complexity of models that we can still add into this, and improving sort of the way we train it, I think we will get to a place where we can be very competitive with conventional data assimilation. But with that, I'm going to hand back to Peter.
Yes, and I'm going to talk about the thing we called hybrid model. So basically, in my intro, I talked about conventional physics-based modeling with the IFS, and Matt then talked about the AFS, where you place the whole thing. But there are also various ways of how you can combine the machine learning model and the conventional physics-based modeling. And so if you have basically this kind of the scale here, and you have 100% physics-based model on the left side and 100% machine learning, so AFS on the right side, there are a lot of different ways how you can basically combine the two worlds. One of them is that you basically do what we call parameterization emulation. So what you basically take is you take a specific component of the IFS, the physics-based model, and just try to learn what the component is doing with a neural network, and then you replace that component with a neural network because it's normally faster and easier to port to GPUs, for example. So the aim in life would then be to kind of basically be as good as a physics-based model, but you would not necessarily get better. However, you can also do other things. Post-processing is kind of very prominent as well. So you take the IFS results and then do post-processing with machine learning. You can either downscale to a specific area to increase resolution, or you can also kind of just make a statistical post-processing of the fields and improve scores. And typically, for example, also kind of take information of the observations or the reanalysis in, and typically you can actually kind of get quite significant improvements of the results then as well. Then there's also another paper that I'm going to come back to later on, where you can also nudge the physics-based models towards the machine learning. So literally kind of run two models in parallel and nudge the one to the other. You can also do bias correction. Then there are different ways of doing bias correction. So basically, you assume your physics-based model, IFS, for example, is very good in principle, but it will have some sort of errors and biases. And you can learn those errors and biases with deep learning. And there's something that we never wanted to do in the past because we were always scared of all the implications this would have on physics-based developments, basically. But it's something that is also kind of fairly interesting because error pattern in particular is something that we can't describe physically, but we can learn it because we can often measure it. So it's something there where really it's kind of getting very interesting for us to look into so-called bias correction methods using machine learning. So there's one that is kind of very close still to the physical modeling. It comes out of 40-var data simulation, where you basically learn the model error within your data simulation cost function and you kind of correct for it. And this kind of can use linear models, for example, but you can also kind of then increase complexity towards neural networks. But there are also other ways. You can, for example, just kind of diagnose the analysis increments. So that's basically when you do data simulation, you detect how far the model is away from the observations that you trust. And then you can basically kind of measure the error of your forecast model. And then you can kind of just learn, like you use the input of the atmosphere as a three-dimensional state, and the output would be then the error prediction. So you can learn the error, and then you can correct for the error in the forecast. And there are some approaches to do this. You can also do the same with analysis. So you can also do a forecast simulation that runs for a couple of days, for example, and then calculate the difference between IFS and the reanalysis and use that as an error pattern to train from. You can also couple machine learning and conventional components. So for example, if you want to kind of have longer forecast horizons, you want to predict like 3 weeks into the future, the ocean will be a very important kind of source of variability in the system. However, the ocean is very expensive as well for those predictions because you typically can go down with the resolution of the atmosphere, but the ocean would still stick at a certain resolution. So why not, for example, couple a machine learned ocean model to a physics-based atmosphere or the other way around? So there are also kind of ways of doing that. And then also you can go a little bit more crazy, a little bit more on the AIFS side and actually learn the whole physics. And this is what I'm going to talk about next, I think. But before doing this, I'll just wanted to make one point here. If you kind of combine physics-based and machine learning models, you will have one problem that you always have with the machine learning models, which is that climate scientists will tell you that you can't really do climate simulations because you're basically leaving the data range of your inputs. So as you kind of have changes in the distributions of input fields as climate change is kind of progressing and temperature is going up, you will leave the kind of framework of your input data set and your training data set, and therefore you may not be able to kind of do predictions here. So there's always the part of you kind of get a lot of downsides as well if you kind of bring the machine learned model into the physical system. But just let's just kind of go into one example here. It's a kind of a paper by Google where I was also involved, and what we've done there, we basically kind of kept the dynamical core. So we kept the part of the forecast model that is describing the fluid dynamical component, basically. So like the general equations on the sphere are still valid, and then we learned what we call the parameterization scheme. So those parts who are actually kind of trying to represent subgrid scale features that we can't resolve properly. And the beauty here is in this kind of specific configuration is that we used as a dynamical core and we made differentiable. So you basically were training correction to the physical fields through the dynamical core based on reanalysis data sets. And we basically kind of propagated the backpropagation of the learning procedures through the dynamical core. So this is kind of really a hybrid approach that kind of is taking the physical system into the training procedure of the machine learning model. And we get quite nice results. And that's also a reason actually why I wanted to show this slide here, because so far those forecast systems like the AIFS and other kind of deep learning tools were only kind of were mostly focusing on the medium range in a couple of days into the future, really up to weeks. But they were kind of less good or less reliable so far on the very long time series of like running it for years and decades, for example. But this system here was actually now able for the first time to kind of run what we call an AMAP simulation. And an AMAP simulation means that you can run an atmospheric model for like decades, and you force it with the ocean as it kind of was observed basically over the time. So you don't really have a climate model yet, but you can actually show that the model simulation is running well for 40 years, I think for 20 years actually of integrations without making anything silly. So it is kind of really another step basically in the developments. However, it's fair to say that those pure machine learning models are kind of now also entering the space. So there's, for example, a model in the US called ACE, where they also kind of have successfully performed AMAP simulations. And if to some extent, this is kind of the first step that you would need to take if you would also want to kind of explore the climate domain with those model simulations. Another approach is actually of this kind of hybrid modeling that you kind of is kind of described on this slide. So one of the general assumptions that we have in physical modeling is that we basically kind of do well on the large scales. So we assume we have a numerical system, we know the equations, so we solve the equations on the grid. And if you then kind of go to the very large scale of the systems, you normally assume that you're doing well because the numerics is kind of well represented, everything is known. So in principle, most of the errors should come from the small scales. And the small scales are where basically we represent subgrid scale features that we can't resolve. And also the numerical methods are kind of getting out of their comfort zone if you really kind of go to less than 5 grid spacings, for example, in your discretization scheme. So in principle, you would assume that if you kind of go to higher resolution, you basically get better prediction. And that's what we've seen in the quiet revolution, kind of really continuing to kind of increase resolution and get better results. However, it now turns out that machine learning actually is doing well, in particular on the coarse resolution, and it's not so well doing so well on the small scales, and it's still competitive. So the machine learning model, this is the plot on the left shows you a spectra of model simulation. So the total wave number goes from low to high, which means that resolution goes from the resolution is kind of the scales are small on the right and large on the left, basically. And you see that a physical model like the GDPS is basically kind of keeping the small scales very well. And then the GraphCast model, the machine learned model, the red line is basically kind of smearing out as Matt as MS told us on the previous slide before. So basically the machine learned model is kind of doing kind of quite good predictions in principle, but getting the small scale wrong. And maybe you can get the best of both worlds, basically, if you kind of nudge the large scales now to the physical model. And that's something where I at the beginning thought this is a silly idea. It should not really kind of help because of this general assumption of the quiet revolution. But actually, it turns out that it helps quite a lot. So there's a Canadian team that kind of published a paper showing that if you nudge the extremely large scales of your physical model to the machine learned model, you actually kind of get really better results. So the red lines here and the plot shows the anomaly so the plot shows the anomaly correlation. The higher, the better. And you see the red line is always on top of the blue line quite significantly. And the red line was a model where they nudged the large scales in particular to the machine learned model. So maybe that's actually also a way of kind of build a physical model where you kind of nudge the large scale of the physical model to the machine learned model. It's also that we can basically learn more about predictability potentially. So, for example, there's another general assumption about predictability of weather that the small scales are the butterflies. So basically, the small scales are those that we cannot really represent in our model systems. But if you're making error in the small scale initial conditions, for example, they will grow exponentially over time in the model integration and become larger and larger, and this will eventually basically destroy our predictability horizon. And the issue is now that as you go to smaller and smaller scales, you will have shorter Lyapunov time scales. So basically, if you could, for example, take a model resolution from 500 kilometers to 250 kilometers, you will still gain a couple of days forecast horizon. If you go from 50 kilometers to 25 kilometers, you probably only gain like a couple of hours forecast horizon. And if you go from 5 to 2.5 kilometers, you may kind of be down to a couple of minutes forecast horizon, in the sense that you kind of get less and less benefit as you increase your resolution in this kind of world of the butterfly effect. And this basically means that there may actually be like a limit in the forecast horizon in principle, a limit where you can kind of cannot go any further because cost is either kind of just exploding for like very kind of diminished returns in terms of the forecast horizon, or even worse, where you will basically kind of just hit the limit of the forecast horizon is kind of converging towards zero, basically. However, there's now a result from machine learned models where they basically show that kind of you can improve your initial conditions by back propagating kind of the model error, and then also kind of by optimizing the initial conditions. So you can basically have a method where you build the optimal initial conditions in principle by kind of using your differentiable machine learning model to kind of optimize the conditions. And they find actually that this is very efficient. So you can actually really kind of get a lot of benefit out of this. And you can actually get forecast horizon of something like 23 days with a deterministic model for this. And that kind of contradicts to some extent the horizon that is limited by Lawrence and others. So in a sense that you wouldn't expect this horizon to be that long. And also what they find out is basically that the biggest improvement that is an improvement that you get from the large scale optimization rather than the small scale optimization. So it's not really that you focus on the small scale to kind of get the butterflies right, but you actually kind of really want to get the large scale patterns right to kind of get the forecast horizon of these kind of very long time scales. And I'm not claiming that this is true now, but I think this is something that you really need to think about if you kind of, for example, think about predictability and how we define this. So I think I'm very much looking forward about the insights that we will get from those machine learned models, for example, in terms of predictability as well, and to kind of also do a lot of studies there that are too cumbersome to perform with a physical model because it's either too expensive or also not really differentiable in the same way, and so on and so forth. So there's a lot of science to be looked at in this area. Just very brief, there's another development that is now coming up that could be potentially kind of quite substantial in how we do science in the area. Which is the one of so-called foundation models. So foundation model is basically an attempt to kind of build a tool that cannot just do one specific task and you have one specific learning procedure, but you actually learn a tool that can do all sorts of different tasks. I brought up my slide from 2020 again, just to show you that there are all these kind of application areas in principle. And the question is, can we build one tool, one big tool that can kind of be helpful in all of those application areas rather than build kind of individual tools for all of those different application areas in principle. And this is what you try to do with a foundation model. And there are kind of approaches like AtmoRep and ClamX, where the people have published in this area in principle already, trying to build a more generic tool that can do a lot of different tasks at the same time. And we will also now start looking into this with a project called Weather Generator that it's a European Union project, quite a large one that will start in February. And our attempt will also be to build those foundation models and to then also kind of apply one model that we trained to kind of build the backbone of the whole learning procedure. And then we will kind of post-process it or kind of fine-tune it for specific application areas. And we will explore to use this tool in 22 application areas in the area of weather and climate. So how does a foundation model work in principle? So the idea is that you basically have like all sorts of different data sets. They can come from reanalysis, they can come from model simulations, or they come from observations. And you basically kind of you will be able to use all of those data sets as inputs. And then you have a very big machine learning model that can do probabilistic mappings, basically. And then once you have done this, you can basically apply this to a lot of different application areas. And so it's kind of not just like a one input, one output type learning procedure, but it's more like a very complex learning procedure that is kind of looking into all sorts of different data sets. There's also another kind of trick to it, which is basically that we will use what we call mask learning. So if you have different data sets, in this case, you have different observations data sets on the y-axis, which is also space, and the time, the x-axis is time evolution. Then you have different availability of those data sets depending on the sources. And the idea now is that you kind of try to learn to map all of those different inputs onto each other. And you do this by basically kind of masking out a specific area in the data set, and kind of you don't mask out the same area for all the different inputs. And then you try to kind of fill in this area back in by supervised learning tasks. And by doing this, you'll basically have a fairly generic learning algorithms where you kind of can go from one data set to the other. And if you, for example, just mask out the right side of this column here, for example, you have a forecast model. If you mask out a specific observation data set, you will kind of have an observation operator. If you mask up a model data set, you will have a data simulation, and so on and so forth. So you can do a lot of different applications with this. I'm running a little bit out of time, so I'm going to skip about this slide here. So there's still a long way. You still need to do a lot of stuff to kind of make this work in principle. But we may end up in a situation where we have like a tool that kind of can do a lot of stuff for domain scientists, and this will also then kind of actually change how a lot of domain scientists will be working. So just imagine that you had basically a hardware somewhere with a lot of data, and the data would kind of include model output, reanalysis data, observations, and all those kind of things, and they would use all the same API and could be easily read into a high-level programming programming language like Python or Jupyter Notebooks or these kind of things. And then think about like off-the-shelf foundation model that basically can kind of transform all these data sets into each other. So if you wanted to transform a satellite data product into ERA, you can do this basically by using this off-the-shelf tool. And this will then allow you to kind of do a lot of different application areas like data simulation, global and limited area models, and also in ensembles, vegetation modeling, whatever you kind of want to look into. And you will also have off-the-shelf solution to kind of do these kind of steps for the different data sets. And then all of those tools that you develop should also be scalable and runnable on a supercomputer, but also on a laptop. So it should also be easy to use. And you should also have like a good understanding of the limitations, also including things like climate runs and these kind of stuff. And basically the weather generator project will kind of cover these points here. The last point up there is basically something for the community, for the bigger community to really think about how to do this. But we are kind of good on track there with kind of projects like Destination Earth, Earth-2, or Eve that kind of really try to kind of build like a general framework for the domain there. I'll skip those slides because I'm really running out of time. We are hiring, so also for the weather generator, but also for other projects. So if you feel interested by this, please have a look at our webpage. And if you feel interested then by the posts that you will see, then please let Matt and myself know. And we're happy to kind of share any information there. So this is a summary slide. We talked about a lot of stuff, so I don't think the summary is particularly useful. So I'm just going to leave it there. And I think Matt and I would be very happy to answer your questions.
Fantastic. Thanks, Peter. Thanks, Matt. That was a very interesting talk, slightly terrifying for someone like me who works on the numerical models. Okay, so we'll open up to questions. You're welcome to type in the chat or unmute yourself and just join in. It's a small enough group that we can just unmute and speak, I think.
I don't believe there are no questions. We're not that bad at presenting.
I don't believe that there are no questions
Someone's
either.
got to be brave enough.
Leonardo, I can see you, but I can't hear you. I can't see you anymore either, but I think you might have been about to type a question.
I have a question, if no one else will.
Yeah, go for it.
So you mentioned when you're talking about the idea of replacing the data simulation with the machine learning, you talked about having a latent space that you might not be able to probe. Does that pose any, I mean, will we be able to have a AI equivalent of like ERA 7 or whatever, or would that be harder to do if we eliminated data simulation completely?
No, I don't think it will mean that we won't be able to get ERA 7. I'm not in any way saying that ERA 7 will be a machine learning product either. You proposed that, not me. I mean, I think this is what you would get from exactly the problem as is framed in that paper, where you're saying the task is sort of almost a deliberately tried to be made difficult by holding out analysis and reanalysis data sets. If you were to train also on reanalysis data sets, you would be able to get a version that you could read out for sort of anywhere in the atmosphere, any variables, and so then you could make a version of this that could be used more in an analysis mode than in a forecasting mode. Already, this can be done because it's been trained on in situ observations at the surface to sort of get a sort of a reanalysis or analysis product, a type product at a point in space at the surface where you've not actually made an observation. So you can start to do this already, sort of read out in different points in space, but you would need to include probably some model data to get the complete aspect of the system.
Thanks.
You can also argue that the reanalysis product is a most difficult task for the machine learning one, because as you go back in time, you have less and less observations, so you have to fill in more and more of your phase space. So it's kind of probably much easier to start from the nowadays analysis and do data simulation there than kind of to go all the way back to the 70s, for example, where you may not have so many observations left.
Yes, Leonardo does have a question. I'll just read it out. He's wondering about the evaluation side of AIFS. The models are evaluated against ground observations for surface variables. But IFS and AIFS provide gridded predictions. How do you evaluate them in practice, and what kind of assumptions or interpolation schemes do you use?
Yes, very, very valid question. So the approach we use at ECMWF, our standard sort of verification approach, would be to take the nearest grid point to where the station was actually, and then do a so-called lapse rate correction, so to correct for the actual station height versus where the model thought it was. So there's a certain sort of post-processing, but not a regridding. This is not really about sort of necessarily saying that either of those two methods are the best way of getting a prediction for that station point, but making a choice on how to do a comparison, because the important thing was to go to an independent data set from both sort of the IFS and AIFS.
I had a quick question about your forecast scorecard that had all the red in the stratosphere. Is that something that you're concerned about and acting to kind of improve? Is it because we have less data in the stratosphere? And does it have an impact on the kind of more long-term predictions of the model?
Lots of good questions, Gemma. I mean, I'm a perfectionist, so any part of red is an absolute atrocity to me. No. So yes, we are. I think there are a couple of reasons why this is the case. One is just the way that the loss is built at the moment. So quite a lot of the models sort of taper off towards the top of the atmosphere, partly saying we should be prioritizing where most people is, and also where the data assimilation is most well constrained. But you could adjust that, and we have a version that we're training at the moment where we weaken that, we strengthen the contribution at the top of the atmosphere, and see that already that improves it. The other thing is just where the model top is at the moment. So the top of these machine learning models is typically at 50 hectopascal. So there's no representation anything above. Not only is it sort of parameterized, but also there's no initial state for what's happening further up in the atmosphere. So if you're thinking about sort of downwards propagating modes like the QBO, you wouldn't have explicit knowledge of that. And so I think we'll also look to move up the model top, and very early signs show that that's already making a big difference. I do think your comment on sort of how well reanalysis constrains that will have an impact, and so it might limit the sort of how good we can get these models. And then what we didn't have time to show here, and it's quite embarrassing for Peter and I, given how much sort of ECMWF prides itself on ensembles, is any of the cool stuff we've been doing on ensembles, because that's where that's one of the next steps of the field is going. That's one of the ways you deal with smoothing, is by framing the problem probabilistically. But we've just started to run some some AIFS ensemble versions out for the extended range, where you would expect sort of perhaps not having good representation of the stratosphere to make a difference. And the early signs are already very competitive with the IFS there. So it's showing that by having a worse representation of that, it's not having a big detrimental effect sort of 3-4 weeks out near the surface. But that doesn't mean to say that if you had a better representation of the stratosphere in the model, you couldn't push the forecast scale further out. So maybe that's a reasonable answer to your question.
Yes, thank you. It's a kind of watch this space answer. So maybe
yes,
we'll have
that's
you
my
back.
hope.
Okay, great. Thank you. Oh, we have another question in the chat. Is there interpretability explainable AI work being done? Some concern about black boxes.
Yeah, that's a great question. I think I'm an interested skeptic about the sort of explainability sort of AI stuff, because I don't think I've really seen it being done at the scale of some of these models, but I would love to be proven wrong. And so I now think there's really an opportunity for some really sort of low-hanging fruit in using some of these explainability techniques, using the fact that lots of these models are open source. The AIFS will go open source very, very soon now, and they would allow you to run some of these particularly gradient-based explainability tools and just see what you get. So actually, if this is something that anyone wants to look at, please send me an email, because I'd love to help sort of test the hypothesis. I'd love to be proven wrong, basically. But to my knowledge right now, there's nothing sort of using sort of conventional machine learning explainability tools on anything of the size of ForecastNet, GraphCast, AIFS. But there should be.
Okay, great. So we're coming to the end of the session. My laptop battery is about to die, so I think that's a sign we should maybe wrap up. Thanks ever so much, Peter and Matt. That was fantastic. If you don't mind pinging me over the slides, I'll update the website later today and put the YouTube link and everything on there. So thanks for a great seminar, and see everybody else in October for the next talk.
Thank you.
Thanks.
Bye-bye.
Bye.